Now, as we know, data is of utmost importance in AI. So let's spend some time to understand the data science process life cycle for the next few minutes. Step 1 in any business problem where we hope to apply AI is just having the right data and having that data cleaned up and organized. If your data is not in good shape, AI tools are likely to be worse than useless. As a matter of fact, you'll likely end up with inaccurate conclusions. A key driver of the rise of the so-called data-driven organization is the increased awareness and use of data-driven decision-making at all levels of business. This is in large part because of the increasing availability and quality of collected data as well as the increasing opportunities to make use of it. As data science and AI make their way into almost every industry under the sun, so do the challenges of building a team capable of building successful AI projects. The demand for that archetypical data scientist, who is the perfect blend of a statistician, programmer, and communicator, has never been greater. But as the dust settles, we have started hearing stories of failed projects and disenchanted professionals. Modern data science teams recognize enlisting business partners in a shared collaboration is essential for delivering business value. They also reorganized that too much analytics models are not deployed or don't deliver the expected business value. Data science teams are adopting decision modeling to address these gaps. As a data scientist consultant who has worked in various industries, I've had the chance to see this trend firsthand. Many people tend to think data science as a new field and expect it to have growing pains as it becomes mainstream, but we forget where the field came from. In the coming few minutes, we will reflect on qualities that make a successful data team and help business leaders and executives create better AI strategies. We will also learn how to think like a data scientist, including taking the steps involved in tackling a data science problem and applying them to interesting real world examples. So let's see, what is data science? Data scientist, the sexiest job of the 21st century. This title has been around for a few years now. I love my job as a data scientist, but is it the sexiest job out there? I love being a data scientist, it's challenging and fun, but about the sexiest part, not so sure. So in this part, you will be learning about the methodology, which is very close to real world experience of working as a data scientist. You will learn how to work on a data science project from developing an idea to deploying it and all the steps in between. The term data scientist came into existence sometime around 2008 when companies began to realize the need for professionals expert at understanding and dealing with data. These professionals could be ranging anywhere from your garden variety statisticians to PhDs. In my opinion, what makes this field particularly interesting is its ability to combine not only the hard sciences of maths, statistics, and computer science, but also the importance of domains such as biology, healthcare, finance, economics, sociology, and the list goes on. So, in simple words, data science is a versatile field that uses scientific methods, processes, algorithms, and systems to extract value from data. Now, let's look at what's a data scientist. Data scientists are experts that use a wide range of skills, including statistics, computer science, and business knowledge, to analyze data collected from multiple sources such as web, smartphones, customers, sensors, and a bunch of other sources. The idea is to reveal trends and produce insights that business can use to make better decisions and create more innovative products and services. Just businesses, you ask? Absolutely not. Data is the bedrock of innovation, and its value comes from the information data scientists can glean from it and then act upon. The role of data scientists has become quite important to businesses. They can be real change makers within an organization, offering insight that can help illuminate the company's trajectory towards its ultimate business goals. Data scientists are integral to supporting both leaders and developers in creating better products and paradigms, and as their roles in big businesses becomes more and more important, they are in increasingly short supply. In terms of credentials, It's not uncommon for a data scientist candidate to have a PhD, but it's not mandatory. Beyond educational credentials, they are expected to use professional skills such as communication, leadership, collaboration, creativity, discipline, and a driving passion for truth in information. A typical day of a data scientist at work includes communicating with business stakeholders to understand their goals and determine how data can be used to achieve those goals. They design data modeling processes, create algorithms and predictive models to extract the insights the business needs. The findings are then shared with peers gained from analyzing the data. While each project is different, the process for gathering and analyzing data generally follows the following path. The first is to ask the right questions to begin the discovery process. Then acquire data, process it and clean it. Moving on, integrate it and store the data. Then we perform some initial data investigation and exploratory data analysis. Choose one or more potential models and algorithms and apply data science techniques such as machine learning, statistical modeling, and AI. The final stage is where we measure and improve the results, present final results to stakeholders, make adjustments based on feedback, and repeat the whole process to solve a new problem. This is what we are going to focus in this section, the data science process lifecycle. It's a recommended lifecycle that you can use to structure your data science, AI, or ML projects. The lifecycle is basically a step-by-step framework or structure that you can use to complete your data science project successfully. This lifecycle is designed for data science projects that are intended to ship as part of intelligent applications. These applications deploy machine learning or AI models for predictive analytics. The lifecycle can explore historical data, make comparisons to competition, analyze the market, and ultimately make recommendations of when and where your product or services will sell best. This can help a company understand how their product helps others and optimize existing business processes. Imagine that you are a data scientist and your first job is to increase sales for a company. The company wants to know what product they should sell in what period. You will need a structure to organize your work, analyze different types of data, and solve their problem. Your customer doesn't care about how you do your job, they only care about the end result. Often there is a temptation to bypass the process and jump directly to solutions. Doing so, however, hinders our best intentions in trying to solve the problem. This lecture has one purpose, and that is to share a process that can be used to ensure that the data used in problem solving is relevant and properly manipulated to address the question at hand. So the question arises, why data science process lifecycle is important? When working with the big data, it is always advantageous for data scientists to follow a well-defined data science workflow. Regardless of whether a data scientist wants to perform analysis with the motive of conveying a story through data visualization or wants to build a data model, the data science workflow matters. Having a standard workflow for projects ensures that various teams within an organization are in sync so that delays can be avoided. The end goal of any data science project is to produce an effective data product. The key insights gathered at the end of a data science project is referred to as a data product. It can be anything, a dashboard, a recommendation engine, or anything that facilitates business decision making to solve a problem. However, to reach the end goal of producing data products, data scientists have to follow a formalized step-by-step workflow. Now, you will learn how to think like a data scientist and take steps involved in tackling data science problem and then applying them to interesting real-world examples. You will also learn the methodical ways of moving from problem to approach, including the importance of understanding the question, the business goals and objectives, and picking the most effective analytic approach to answer the question and solve the problem. You will learn the systematic ways of working with data, specifically determining the data requirements, collecting the appropriate data, understanding it, and then preparing it for modeling. You are going to learn how to model the data by using the appropriate analytic approach based on the business requirements and the problem that you are trying to solve. Now, once the approach is selected, You will learn the steps involved in evaluating and deploying the model and getting feedback on it, and using that feedback constructively so as to improve the model. The success of any data science project will depend on how closely we follow this process. So next, we'll cover the first step of data science process lifecycle, that is business understanding, and you will see how important it is to have a business understanding and why we should identify the key objectives that the business is trying to uncover. So now we are in the business understanding stage. Give me data and I can do wonders. This is a common fallacy we see today amongst data scientists. Many data scientists today miss a crucial step of understanding the business and how underneath data was generated from the business process before playing around with data. While jumping onto the data is not bad all the time, but in most cases we end up with insights that do not get integrated with real world instances. Business understanding is very important before jumping in. There are multiple pitfalls of not having an understanding of business and underneath data, such as trying to solve business objectives other than actual one that can impact the business significantly, insights that do not generate any significant value even after it gets into production. Business and data scientists acting in complete vacuum often results in business development skew. And to state an example, I knew a marketing team who had a problem with low conversion rates for acquiring new prospects. They were also spending a high cost to acquire prospects that were taking more time for them to turn positive post prospects into their customers. The data scientist team got internal CIO funding and related datasets to solve the problem. So here is how it went wrong. Business stakeholders were consulted minimally to clarify data elements rather than understanding the business process or real challenges within the business environment. The resultant model that was developed did slightly better than the current conversion rate in the validation phase. Excited CIO and data scientist team put forward this finding to business, explaining what they did, and it turned out that the marketing team challenge was not the low conversion rate. While they would have loved to increase the conversion rate, their immediate problem was not to prioritize prospects to understand where to spend more and where not. There was a lack of customization to individual prospects in terms of products or offers. So, coming to the point, by not working on clear business objectives or agreeable success criteria, the data science project failed before it even started. In business understanding phase, we define goals. Here, we specify the key variables that are to serve the model targets and whose related metrics are used to determine the success of the project. We identify the relevant data sources that the business has to access to or needs to obtain. So, the question is how to define goals. Now, there are two main tasks addressed in this stage. So, defining objectives. Here, we work with our customer and other stakeholders to understand and identify the business problems. We formulate questions that define the business goals, and the data science techniques can target. A central objective of this step is to identify the key business variables that the analysis needs to predict. We refer to these variables as the model targets, and we use metrics associated with them to determine the success of the project. Two examples of such targets are sales forecast or the probability of an order being fraudulent. We define the project goals by asking and refining sharp questions that are relevant, specific, and unambiguous. Data science is a process that uses names and numbers to answer such questions. You typically use data science or machine learning to answer 5 types of questions. So these are how much or how many, which is regression. Then we have which category, which comes under classification. Next question is which group, that is clustering. Then we have is this weird, so this comes under anomaly detection. The last question is which option should be taken, and this comes under recommendations. So the first thing that you need to do is, after having the objective set as per the business understanding, you need to determine which questions you are asking and how answering it achieves your business goals. And then we define or create the project team by specifying the roles and responsibilities of its members, and develop a high level milestone plan that you can iterate on as you discover more information. Now, once the team, role, and responsibilities are discussed, we define the success metrics. For example, you might want to achieve a customer churn prediction and you need an accuracy rate of X% by the end of this 3-month project. With this data, you can offer customer promotions to reduce churn. The metrics must be SMART, that means specific, measurable, achievable, relevant, and time bound. And then comes data into the picture. Not actual data, but identifying the data sources. Here we look for the relevant data that helps you answer the questions that define the objectives of the project. We look for data that's relevant to the question. We see if we have the measures of the target and features that are related to the target. So here are some deliverables at this stage. A charter document. The charter document is a living document that you can update the template throughout the project as you make new discoveries and business requirements change. The key is to iterate upon this document, adding more detail as you progress through the discovery process. Keep the customer and stakeholders involved in making changes and clearly communicate the results for the changes to them. Then we have the data sources report. The raw data sources report specifies the original and destination locations for the raw data. In later stages, you will fill in additional details like the scripts to move the data to your analytic environment. Then we have the data dictionaries. This document provides descriptions of the data that's been provided by the client. So these descriptions include information about the schema, that means the data types, and information on the validation rules if any, and the entity relationship diagrams if available. Thus, by working on having a sound business understanding, structured discussions can take place where priorities can be identified in a way that can lead to organizing and planning on how to tackle a problem. Depending on the problem, different stakeholders will need to be engaged into the discussion to help determine requirements and clarify questions. So you might have gained a good understanding of how important this stage is for the success of your data science project. Having a business understanding of the problem and identifying data resources are two important things that we will discuss in the next stage. So next we are going to look at the next stage in the life cycle, which is the analytic approach. So you now know the business problem and the questions. So the next stage is analytics approach. How can you use the data to answer the question? Selecting the right analytic approach depends on the questions being asked. Once the problem to be addressed is defined, the appropriate analytic approach for the problem is selected in the context of the business requirements. This is the second stage of the data science process lifecycle, and this step entails expressing the problem in the context of statistical and machine learning techniques, and it is essential because it helps identify what types of patterns will be needed to address the question most effectively. The analytical options may include statistical analysis applies to problems that require counts. If the question is to determine probabilities of an action, then a predictive model might be used. If the question is to show relationships, a descriptive approach may be required. If the question entails a yes or no answer, then a classification approach to predicting a response would be suitable. So let's take a look at a simple example. Suppose we have mails to classify which we receive in our email ID to spam and non-spam. So the basic question is whether the mail received is a spam or a non-spam. So we shall use the classification model as it gives us a yes or a no. If the result comes as yes, the mail shall go to the spam folder, and if no, it should be delivered as normal mail in our inbox. There are 4 types of analytics here. We start with the simplest one and go further down to the more sophisticated types. So as it happens, the more the complex an analysis is, the more value it brings out. So we have descriptive analytics, and this answers the questions of what happened. So let us see an example. Having analyzed monthly revenue and income per product group, the total quantity of metal parts produced per month, a manufacturer was able to answer a series of what happened questions and decide on focus product categories. Descriptive analytics juggles raw data from multiple data sources to give valuable insights into the past. However, these findings simply signal that something is wrong or right without explaining why. For this reason, data consultants don't recommend highly data-driven companies to settle for descriptive analytics only. They'd rather combine it with other types of data analytics. The next is diagnostic analytics. At this stage, historical data can be measured against other data to answer the question of why something happened. For example, a retailer can drill the sales and gross profit down to categories to find out why they missed their net profit target. Another example in the healthcare industry would be customer segmentation coupled with several filters applied like diagnosis and prescribed medications, allowing identifying the influence of medications. So diagnostic analytics gives in-depth insights to a particular problem. At the same time, a company should have detailed information at their disposal. Otherwise, data collection may turn out to be individual for every issue and time consuming. Then we have predictive analytics. This tells us what is likely to happen. It uses the findings of descriptive and diagnostic analytics to detect clusters and exceptions and to predict future trends, which makes it a valuable tool for forecasting. For example, we can help a leading FMCG company to predict what they could expect after changing brand positioning, and predictive analytics belongs to advanced analytics types and brings in many advantages like sophisticated analysis based on machine or deep learning and proactive approach that predictions enable. However, forecasting is just an estimate, the accuracy of which highly depends on the data quality and stability of the situation, so it requires careful treatment and continuous optimization. At last, we have prescriptive analytics. The purpose of prescriptive analytics is to literally prescribe what action to take to eliminate a future problem or to take full advantage of a promising trend. An example of prescriptive analytics is a multinational company was able to identify opportunities for repeat purchases based on customer analytics and sales history. So, prescriptive analytics uses advanced tools and technologies like machine learning, business rules, and algorithms, which makes it more sophisticated to implement and manage. Besides, this requires not only historical internal data but also external information due to the nature of algorithms it's based on. That is why, before deciding to adopt prescriptive analytics, I strongly recommend weighing the required efforts against an expected added value. So, the next stage that we'll cover now is the third stage of the data science process lifecycle, which is data requirements. You'll see how important it is to discover the correct data for your model. So, we understood the analytic approach and how certain problems require certain analytic approaches to be applied. So, if your goal is to make a spaghetti dinner but you don't have the right ingredients to make this dish, then your success will be compromised. Think of this section of the data science methodology as cooking with data. Each step is critical for making the meal. So, if the problem that needs to be resolved is the recipe, so to speak, and data is an ingredient, then the data scientist needs to identify which ingredients are required, how to source or collect them, how to understand or work with them, and how to prepare the data to meet the desired outcome. Building on the understanding of the problem at hand and then using the analytic approach selected, the data scientist is now ready to get started. The data requirements analysis process employs a top-down approach that emphasizes business-driven needs. So the analysis is conducted to ensure that the identified requirements are relevant and feasible. The process incorporates data discovery and assessment in the context of explicitly qualified business data consumer needs. Having identified the data requirements, candidate data sources are determined and their quality is assessed during the data quality assessment process. Any inherent uses that can be resolved immediately are addressed using the approaches, and those requirements can be used for instituting data quality control. The data requirements analysis process includes these phases. First one is identifying the business context, and this step includes 5 subparts, which is identifying the relevant stakeholders, and this can be done through a review of existing system documentation, or they may be identified by the data quality team through discussions with business analysts, enterprise analysts, and enterprise architects. Then we acquire the documentation. So in this step, the data quality analyst must become familiar with the overall goals and objectives of the target information platforms to provide context for identifying and assessing specific information and data requirements. Then comes documenting goals and objectives. At this stage, we determine existing performance measures and success criteria that provide a baseline representation of high-level system requirements for summarization and categorization. Then we summarize the scope of capabilities. So here we create graphic representations that convey the high-level functions and capabilities of targeted systems, as well as providing details of the functional requirements and target user profiles. Finally, we document the impacts and constraints. So here the constraints are conditions that affect or prevent the implementation of system functionality, whereas impacts are potential changes to characteristics of the environment to accommodate implementation of system functionality. The second stage is we move on to the phase of conducting stakeholder interviews. Over here, we review existing documentation, and this only provides a static snapshot of what may be true or not true about the state of the data environment. A more complete picture can be assembled by collecting that might be deemed hard evidence from the key individuals associated with the business processes that use data. Therefore, our next phase would be to conduct conversations with the previously identified key stakeholders, note their critical areas of concern, and summarize those concerns as a way to identify gaps to be filled in the form of data requirements. The third stage would be synthesizing expectations and requirements. The next phase synthesizes the results of the documentation scan and the interviews to collect metadata and data expectations as part of the business process flows. So, the analyst will review the downstream applications use of business information to identify named data concepts and types of aggregates and associated data element characteristics. The fourth is developing source to target mappings. Here, the goal of source to target mapping is to clearly specify the source data elements that are used in downstream applications. In most situations, the consuming applications may use similar data elements from multiple data sources. The data quality analyst must determine if any consolidation and/or aggregation requirement are required and determine the level of atomic data needed for drill down, if necessary. Any transformations specify how upstream data elements are modified for downstream consumption and business rules applied as part of the information flow. So during this phase, the data analyst may identify the need for reference data sets. This provides a good starting point in the data requirements analysis process that can facilitate the data selection process. So with this, the data requirement stage for the data science process lifecycle ends. Now this brings us to the next step of data collection. So now that we have a solid idea of our questions, so it's time to define what data you need to find those answers. So where is the data coming from and how to get it? As a starting point, you will want to determine if the data is readily available within your organization. Then ask yourself, do you have all the data that you need, or you will need to externally source it? If it's the latter, then you might need to decide to run an experiment or conduct another survey. Whatever you choose, the end goal of this step is to make sure that you have complete 360-degree view of the problem that you want to solve. So where does this data come from? We have two choices: observe the data from existing sources or generate the data via surveys, simulations and experiments. Let's take a closer look at how both approaches work. So the first approach is found or observed data. To get this data from the internet, there are multiple options. We can use bulk downloads from websites such as Wikipedia, IMDb, Million Song Database, etc. Or we can access the data through API like APIs for New York Times, Twitter, Facebook, Foursquare, or we can use web scraping to scrap public, non-sensitive and anonymized data. With humongous data, only machines can get effective insights. Listening to huge streams of data from multiple sources at multiple infrastructure layers, learning engine can discover trends and patterns and identify abnormalities. The second approach would be to generate data. An alternative approach is to generate data by yourself, for example with a survey. In a survey design, we have to pay attention to data sampling, that is, who are the users completing the survey and we can only get the data from the users who are accessible and willing to respond. Also, users can provide answers that are in line with self-image and researchers' expectations. Next, data can be collected using simulations, where a domain expert specifies a behavior model of users at a micro level. For instance, crowd simulation requires specifying how different types of users will behave in a crowd. For example, following the crowd, looking for an escape, etc. The simulation can be run under different conditions to see what happens. The process of generating data is often already established. Usually, there is a monitoring tool plugged in collecting key performance indicators that we want to track. So, if we want to generate additional data, we need to invoke or write additional scripts measuring, querying, and logging them. Thus, finding the data is not the problem. The real challenge is which data to collect and how not to be overwhelmed by the useless noise. Collecting detailed metrics from the systems, both on the application and infrastructure side, specialists need to look at tracking data from many sources. It is important to understand the capabilities and limitations of each data source so that you can determine its applicability for your organization. In gathering large volumes of data, we need to leverage this data and build an adaptive system that is more proactive and less reactive. The more the system can learn from the data, the better it can identify variances and problem areas in a timely manner to help fix issues before it negatively impacts the business with poor performance or downtime. The data requirements and data collection stages are extremely important because the more relevant data you get, the better you build your model. The more data collected at a detailed level, the more accurate will be the predictions, providing insights and inferences for a variety of use cases. So once the data ingredients are collected, then in the data collection stage, the data scientist will have a good understanding of what they will be working with. In the next stage, we will see techniques such as descriptive statistics and visualizations can be applied to the dataset to assess the content, quality, and initial insights about the data. Gaps in data will be identified and plans to either fill or make substitutions will have to be made. In essence, the ingredients are now sitting on the cutting board. Now that the data collection stage is complete, data scientists use descriptive statistics and visualization techniques to understand data better. But first, let's see what is data understanding. Data understanding encompasses all activities related to constructing the dataset. Essentially, the data understanding section of the data science process lifecycle answers the question, is the data that you have collected representative of the problem to be solved? Data understanding is the knowledge that you have about the data, the needs that the data will satisfy, its content and its location. To be clear, it is much more than current location and a definition of what a data element means within an application or database. There is no tool or artifact for data understanding. Data understanding is expressed in organizations as business glossaries, data dictionaries, models, and other forms of metadata or other places where information about the data is stored. In order to get to know our data better, we create a few reports. Like we have the initial data collection report, and here we list the datasets or data sources acquired together with their locations, the methods used to acquire them, and the problems encountered. Record problems encountered and any resolutions achieved. So this will aid with future replication of this project or with execution of similar future projects. Then we have the data description report. In this report, we describe the data that has been acquired, including the format of the data, quantity of the data, for example, the number of records and fields in each table, the identities of the fields, and other surface features that have been discovered. We evaluate whether the data acquired satisfies the relevant requirements. Then we have the data exploration report, and here we address the data mining questions using querying, visualization, and reporting techniques. Data scientists explore the dataset to understand its content and determine if additional data is necessary to fill any gaps, but also to verify the quality of the data. In data understanding stage, data scientists try to understand more about the data that we've collected before, and we have to check the type of each data to learn more about their attributes and their names. So, in order to understand the data, we use descriptive statistics on the variables or columns. These statistics may include univariates, mean, median, mode, minimum, maximum, and standard deviation. The pandas.describe function provides a good descriptive statistics summary. A firmographic data understanding is also relevant at this stage, as well as pairwise correlation to see how closely related variables are, and dropping variables that may be highly correlated, hence redundant, leaving only one such for modeling. Visualization libraries such as Matplotlib and Seaborn could be used to gain better insights about the data. Missing value evaluation is also done at this stage. We address questions such as, is the data complete? Does it cover all the cases required? Is it correct, or does it contain any errors? If there are any errors, how many are there? How common are they? Are there any missing values in the data? If so, how are they represented? Where do they occur, and how common are they? Therefore, in this report, we list the results of the data quality verification. If quality problems exist, we list possible solutions. Solutions to data quality problems generally depend heavily on both data and business knowledge. And furthermore, we include first findings or initial hypotheses and their impact on the remainder of the project. If appropriate, include graphs and plots to indicate data characteristics that suggest further examination of interesting data subsets. So in conclusion, the main goal of data understanding is to gain general insights about the data that will potentially be helpful for further steps in the data analysis process. But data understanding should not be driven exclusively by goals and methods to be applied in later steps. Although these requirements should be kept in mind during data understanding, one should approach the data from a neutral point of view. Never trust any data as long as you have not carried out some simple plausibility checks. The more one works with the problem and the data, the more one learns, and therefore the more refinement that can be done with the model, ultimately leading to a better solution to the problem. So this ends the data understanding step of the data science process lifecycle. Now, before data scientists begin exploring their data with analytic tools and reports, they must complete data preparation as a first step. So what does this exactly mean? Consider how a chef uses the technique mise en place, which translated from French means everything in place. So for the process of cooking, this means getting all the ingredients measured and ready in mixing bowls and tools out and available, and all the vegetables cut up. Only when that work has been completed is the chef ready to start with the step 1 of the recipe without having to pause and look for any ingredient or tool. So data preparation is the equivalent of mise en place but for analytics projects. Put simply, data preparation is the process of taking raw data and getting it ready for ingestion in an analytics platform. To achieve the final stage of preparation, the data must be cleansed, formatted, and transformed into something digestible by analytics tools. These are broad strokes, and actual process can include a wide range of steps, such as consolidating or separating fields and columns, changing formats, deleting unnecessary or junk data, and making corrections to data. To get a better sense of what's involved with data preparation, let's take a look at what some of these individual steps involve. So first, we delete unnecessary data. So when juggling with different data sets, it's common for extra or unnecessary fields to be used across different sources. To cleanly consolidate different data sets into a workable analytics platform, the fields must match up, which means streamlining and aligning so things are in sync. Then we have consolidating or separating fields. So if you've got data coming in from several different sources, it's possible that each one uses different formats for writing geolocations. For example, one source might have a street address with both number and name in a single field, while other source might separate the two. Proper analysis requires consistency across fields, so the address data needs to be either consolidated or separated based on preference. Then we have transforming the data. In this step, let's take the example of Internet of Things devices. Perhaps you want to run an analysis on errors signaled cumulatively across devices. However, the error codes are in single-digit format, which makes it hard to think about a real-world perspective. Data transformation is the process of translating those error codes into descriptions and messages that can be much more easily deciphered. Then we make corrections to the data. Assume you have consolidating datasets from 3 different IoT devices, all reporting with timestamps. You know that one particular dataset consistently has a time lag in all of the values. So in order to accurately use that data, those datasets must be corrected. Then we can change the formats. So timestamps are a good example of having different formats across multiple sources. For example, North American timestamps usually use the format of MMDDYY, but many other countries use the standard YYMMDD, and transforming this data into one consistent format is necessary for creating a single usable dataset. So now let's look at the benefits of data preparation. So what does all the time and effort do for the data scientist that is gone in data preparation? So it's all about confidence in the data, confidence in the process, and confidence in the insights derived from the data. Data preparation ensures accuracy in the data, which leads to accurate insights. Without data preparation, it's possible that the insights will be off due to junk data, an overlooked calibration issue, or an easily fixed discrepancy between datasets. Going back to the idea of cooking, how many chefs would fare without mise en place? Perhaps they'd be left scrambling for the right tools while the meat is browning, thus causing it to burn. Or they'd discovered that their bell peppers had gone bad, except the recipe is short because they are halfway through the process. Mise en place is necessary for smooth and successful cooking, and at the same time, and it's the same thing when handling big data. Data preparation is often the most important step of any analytics project. The data preparation phase sets the stage for the next steps in addressing the question. So, while this phase may take a while to do, if done right, the results will support the project. And if this is skipped over, then the outcome will not be up to par and you may have to go back to the drawing board. Now, modeling is the stage in the data science process lifecycle where the data scientist has the chance to sample the sauce and determine if it's bang on or it's in need of more seasoning. So once the data is prepared for the chosen machine learning algorithm, we are ready for modeling. In the modeling stage, the data scientist has a chance to understand if his work is ready to go or if it needs to be reviewed. Modeling is geared towards answering two questions: what is the purpose of data modeling, and what are the characteristics of the process? The modeling stage focuses on developing models that are either descriptive or predictive, and these models are based on the analytic approach that was statistically taken or through machine learning. The definition of a model, according to Merriam-Webster, is a system of postulates, data, and inferences presented as a mathematical description of an entity or state of affairs. That said, models aren't exclusive to the math genius and the computer whiz. You probably make use of models every day. For example, while driving during your morning commute, do you try to find the fastest lane? Maybe you consider moving to the lane furthest from an on-ramp to avoid congestion, or you move to the lane closest to an upcoming off-ramp because there are fewer cars in that lane. In driving the same road over and over again, you've learned more about the system, ramp location, traffic congestion, driver behavior, and as you have learned, you've made modifications in your behavior to optimize your drive time. A data scientist's model does the same thing. The data is your experience driving, a computer is your brain trying different driving patterns to learn what works best, and the model is an equation of data inputs affecting a target value. In this case, the target value is how long you take to get to work. These models are based on the analytic approach that was taken, either statistically driven or machine learning driven. The data scientist will use a training set for predictive modeling. A training set is a set of historical data in which the outcomes are already known. The training set acts like a gauge to determine if the model needs to be calibrated. In this stage, the data scientist will play around with different algorithms to ensure that the variables in play are actually required. The success of data compilation, preparation, and modeling depends on understanding of the problem at hand and the appropriate analytical approach that has been taken. The data supports the answering of the question, and like the quality of ingredients in cooking, sets the stage for the outcome. Constant refinement, adjustments, and tweaking are necessary with each step to ensure that the outcome is one that is solid. So data modeling focuses on developing models that are either descriptive, predictive, or prescriptive. Descriptive modeling is a mathematical process that describes real-world events and the relationships between factors responsible for them. For example, a descriptive model might examine things like if a person did this, then they are likely to prefer that. Then we have predictive modeling, which is a process that uses data mining and probability to forecast outcomes. For example, a predictive model might be used to determine whether an email is a spam or not spam. For predictive modeling, data scientists use a training set that is a set of historical data in which outcomes are already known. This step can be repeated more times until the model understands the question and answers to it. Then we have prescriptive modeling that takes into account all inputs, processes, and outputs, and models are calibrated and validated to ensure that they accurately reflect business processes. Prescriptive models recommend the best way forward and actionable information to maximize overall returns and profitability. Prescriptive analytics models support informed decision making. The success of data compilation, preparation, and modeling depends on the understanding of the problem at hand and the analytical approach being taken. The data supports the answering of the question at hand, and the quality of the ingredients in cooking sets the stage for the outcome. The end goal is to move the data scientist to a point where a model can be built to answer the question. Now, the model evaluation stage goes hand in hand with model building. As such, model creation and evaluation are done iteratively. Model evaluation is performed during model development and before the model is deployed. Evaluation allows the quality of the model to be assessed, and it's also a way to see if it meets the initial request. Evaluation answers the question, does the model used really answer the initial question, or does it need to be adjusted? So model evaluation can have two phases. The first is diagnostic measures phase, which is used to ensure that the model is working as intended. If the model is a predictive model, a decision tree can be used to evaluate if the answer the model can output is aligned to the initial design. It can be used to see where there are areas that require adjustment. If the model is a descriptive one, then we see relationships that are being assessed, and then a training set with known outcomes can be applied, and the model can be refined as needed. The second phase of the evaluation that may be used is statistical significance testing, and this type of evaluation can be applied to the model to ensure that the data is being properly handled and interpreted within the model. This is designed to avoid unnecessary second guessing when the answer is revealed. In the model evaluation stage, the data scientists can evaluate the model in two ways: holdout and cross-validation. So in the holdout method, the dataset is divided into three subsets: a training set, as we said in the modeling stage, a validation set, that is a subset used to assess the performance of the model built in the training phase, and a test set is a subset to evaluate the likely future performance of a model. In the cross-validation method, you simply sample a dataset, train the model using the remaining part of the dataset, use the reserve sample of the test or validation set, and this will help you in gauging the effectiveness of your model's performance. If your model delivers a positive result on validation data, go ahead with the current model. Model evaluation entails computing various diagnostic measures and their outputs such as tables and graphs, enabling the data scientist to interpret the model's quality and its efficacy in solving a problem. For a predictive model, the data scientists use a testing set, which is independent of the training set but follows the same probability distribution and has a known outcome. The testing set is then used to evaluate the model so that it can be refined as needed. Sometimes the final model is applied also to a validation set for a final assessment. In addition, data scientists may assign statistical significance tests to the model as a further proof of its quality. The additional proof may be instrumental in justifying the model's implementation or taking actions when the stakes are high, such as an expensive supplemental medical protocol or a critical airplane flight system. So the idea of building machine learning models works on constructive feedback principle. You build a model, you get feedback from the metrics, make improvements, and you continue until you achieve a desirable accuracy. So the evaluation metrics explain the performance of a model, and an important aspect of evaluation metrics is their capability to discriminate amongst model results. I have seen plenty of analysts and aspiring data scientists not even bothering to check how robust their model is. Once they are finished building a model, they hurriedly mapped predicted values on unseen dataset, and this is an incorrect approach. Simply building a predictive model is not your motive. It's about creating and selecting a model that gives high accuracy on your test data. Hence, it is crucial to check the accuracy of your model prior to computing the predicted values. In our industry, we consider different kind of metrics like precision, recall, area under the curve or AUC, etc. to evaluate our models. The choice of metric completely depends on the type of model and the implementation plan of the model. This concludes the model evaluation stage of the data science process lifecycle. So, is your model now ready to be put in practice? Before you think about what tools you need to deploy your model, you need to have a firm grasp on what deployment means. To attain that understanding, it's helpful to put yourself in the shoes of a software engineer. So how does a software engineer think about deploying code? How does the concept of deploying code transfer to the domain of machine learning? Thinking about deployment as a software engineer rather than a data scientist will dramatically simplify what it means to deploy a model. To understand what it means to deploy an ML model, let's briefly discuss the life cycle of an ML project. So hypothetically, a product manager will discover some user need and determine that machine learning can be used to solve this problem. This will involve creating a new product or augmenting an existing product with machine learning capabilities, typically in the form of a supervised learning model. The product manager will meet with an ML team lead to plan the project by defining the project goals, choosing a metric, and setting up the code base. If appropriate training and validation data exist, the project will be handed off to the data scientists or ML engineers to handle the iterative process of feature engineering and model selection. The goal at this stage is to build a model with a level of predictive performance that meets or exceeds the goal set during the planning stage. Throughout the initial stages, the user's needs that motivated this project are still unmet. These needs won't be satisfied even when a model exists that achieves the minimum required level of predictive performance. A machine learning model can only begin to add value to an organization when the model's insights routinely become available to the users for which it was built. The process of taking a trained model and making its predictions available to the users or other systems is known as deployment. Deployment is entirely distinct from routine machine learning tasks such as feature engineering, model selection, or model evaluation. As such, deployment is not very well understood amongst data scientists and ML engineers who lack the backgrounds in software engineering or DevOps. But luckily, these skills aren't very difficult. With practice, any data scientist can learn how to deploy their models to production. So let's see a deployment example of a lead scoring model. So suppose a data scientist has built a lead scoring model for a group of technical analysts who are well versed in SQL. So the analysts seek to group new leads into a bucket based on their likelihood of converting into customers. Each morning, they would like to use data from the database to create or update dashboards they maintain in a BI tool. Since the analysts know SQL and expect model scores to be stored in a database, deploying the lead scoring model means generating daily lead scores for the new leads and storing these in the analyst database. The key aspect about deployment are predictions that can be generated on a group of new leads. These predictions need to be made available each day and the predictions need to be stored in a database. The deployment process needs to satisfy three constraints in order for the ML model to add value to the business. While the data science model may present a solution, the key to making the solution relevant and useful to the initial problem is to get the stakeholders acquainted with the tool produced. This stage requires effective communication skills for onboarding. The model may be deployed to a limited number of stakeholders initially or to a test environment to build up confidence in applying it for use across the board. The model must be relatively intuitive to use, and staff members who may be responsible to apply the model to solve similar problems must be trained. it is important to document teething problems that may arise at this stage. Data scientists have to make the stakeholders familiar with the tool produced in different scenarios. So once the model is evaluated and the data scientist is confident that it will work, it is deployed and put to the ultimate test. So the deployment stage depends on the purpose of the model, and it may be rolled out to a limited group of users in a test environment. A real case study example can be for a model destined for the healthcare system. The model can be deployed for some patients with low risk and afterwards for high risk patients too. Once the model is evaluated and the data scientist is confident that it will work, it can be deployed and put to the ultimate test. So depending on the purpose of the model, it may be rolled out to a limited group of users or in a test environment to build up confidence in applying the outcome for use across the board. And now, once the model is deployed, feedback from the users will be used to refine the model and assess it for performance and impact. So this will continue for as long as the solution is required. The feedback process is based on the notion that the more you know, the more you'd want to know. And this stage involves gathering new data from the field to further develop the model. The feedback stage is usually made the most from the customer, and the customers after the deployment stage can say if the model works for their purposes or not. Data scientists can take this feedback and decide if they should improve the model. That's because the process from modeling to feedback is highly iterative. It can be ongoing for months. So be prepared to loop all the way back to the start of the process and repeat any steps. Once the customer gets a better understanding of the undertaking, they will have more questions for you to explore. So by collecting the results from the implemented model, the organization gets feedback on the model's performance and its impact on the environment in which it is deployed. For example, feedback could be taken in the form of response rates to a promotional campaign targeting a group of customers identified by the model as high potential responders. Analyzing this feedback enables data scientists to refine the model to improve its accuracy and usefulness. They can automate some or all of the feedback gathering and model assessment, refinement, and redeployment steps to speed up the process of model refreshing for better outcomes. So, when the model meets all the requirements of the customer, our data science project is complete. The final curtain, or so it may seem. I won't go into too much depth here, but at least we put everything into a report and make an accompanying presentation. One important thing to note here is that in your report you should always outline options for future direction, and these can bring things that were discovered and could warrant further investigation, and this means potential project extensions. So more work is always good in any situation, right? And this ends our feedback part of the data science process lifecycle. So this is where we will stop with the lecture now, and next time we will get into a hands-on demonstration using the Jupyter Notebook on the data science process lifecycle.